All right, so before we get started on our next chapter's worth of material, we all just had our first exam, okay? Please take today's daily quiz to let me know sort of how it goes and give me some feedback as to how the course is going in general. In addition to our course content, we also have our Chemistry in Careers project. Just to note that the way that the project was designed was to leave the whole month of November open for you to do those interviews. If you want to do them earlier, you're more than welcome to. So every assignment up until publishing that interview has been opened up. Please just make sure to follow the guidelines for the questions that you need to be asking, right? So there's an assignment there to help you build your interview questions. Sucks to do an interview and then not ask any of the questions you were supposed to ask, right? So please just make sure that you're following that assignment more or less in order so that you've got the correct content. But yes, if you want to knock your interview out now, go for it. Cool. All right, so we're going to start this chapter by talking about aromatic compounds. That's the title of our chapter here. And we're kind of going to build up to what this means by aromatic by the end of the day, all right? What we're first going to do is spend a bunch of time talking about what is like the quintessential organic molecule aromatic molecule in organic chemistry, what's known as benzene. All right, benzene plays a little bit of an outsized role in organic chemistry, in the history of organic chemistry, because it was really important in developing certain theories, one of which is this concept of aromaticity, which we'll go over. A benzene ring is a cyclohexane ring, but then every other bond is a double bond here. All right. Benzene, again, it plays a really important role in the history of organic chemistry. Most organic chemistry labs now don't use benzene itself. They try to use some sort of a derivative, like stick a methyl group on there or something like that. And we'll talk about a few of those derivatives. The reason why they've sort of steered away from benzene itself is because after many years of study, we realized that it is absolutely horrible for you in terms of its ability to seep into your cells and work its way into your DNA. It is just a textbook carcinogen. So when we can avoid using it, we do. We're gonna stick little functional groups on there, modify it a little bit to make it a little bit more safer, and we'll talk about these modifications. All right, but a lot of this theory is built around benzene itself here. So this is kind of gonna be where we start our discussion. All right, I obviously did the bond line structure of benzene. Okay, everybody take a second and give me this chemical formula here, given this bond line structure. All right, I think we can all hopefully see that we have 6 carbons. How many hydrogens do we have? So let's look at each one here. If I'm looking at this carbon, for example, currently I see 1, 2, 3 bonds, so then that 4th one must be that hydrogen. And so absolutely, each one of these carbons has just 1 hydrogen sticking off of it. So my molecular formula here for benzene would be C6H6. So if I'm going to sort of draw out the Lewis structure where I have to include all those hydrogens, okay. And importantly, we're going to talk about benzene and its geometry. Similar to where we started for alkenes, we were able to identify what atoms lie in this plane about that double bond. All right, so let's just take one, actually let's take a look at a simple alkene here and remind ourselves. Okay? We said that these carbons about these double bonds, they have this specific hybridization we call an sp2 hybridization. And that leads to this trigonal planar geometry. So one of the first things we did was we talked about the geometry of these alkenes, and we said, all right, trigonal planar, which one of these atoms lie in the same plane in this molecule? Okay, and it was these sp2 hybridized carbons, so the carbons on either side of the double bond, as well as what? How many total atoms should I have colored here? 6, right? So not only my sp2 hybridized carbons, but also both of their bonds. All of these atoms lie in the same plane. And we talked about how that influenced the reactivity of those molecules. They're really flat about that double bond region, making those double bonds really accessible. Okay? Let's apply this same logic to benzene here. Let's just take this double bond as an example. Okay, again, I should have these 6 atoms colored that are all in the same plane. The 2 about the double bond, as well as their 2 bonds. Cool. So now let's jump to the other double bond. Again, I have these 2 carbons about that double bond that are in the same plane. I already got 1 colored, as well as their 2 bonds. All right, and then we go to our last double bond. Again, my 2 carbons about my double bond, as well as those 2 hydrogens. Okay, so in terms of the geometry of our benzene, the entire molecule, all 12 atoms in this molecule are lying in one flat disk. Okay, so our geometry of benzene is completely flat. All 12 atoms are in the same plane. All right, this is part of why it's so terrible for you, is because this really flat molecule is able to work its way in between your double helix in your DNA and just kind of kinks it a little bit, just kind of messes it up ever so slightly. That means that any gene that needs to be read is not really read correctly. All right, that's kind of a classic feature of a carcinogen. They work your way into your DNA double helix. So again, benzene, kind of terrible for you. One reason why is because it is completely flat. It's got that flat geometry, just like we discussed for our regular old alkenes. Okay? What makes benzene so special here is the number of double bonds, as well as the fact that they're connected in this ring. Okay? We'll talk a little bit more about that here in a second. The first place we're going to start with benzene is the first place we start with all of our new functional groups, all of our new compounds, and that is nomenclature. Right, so obviously if I gave you this molecule right here and I asked for the name, what would you tell me? Benzene, cool. So now how do we name it when we start sticking different groups on there? All right, so I'm going to stick a propyl group on here. All right, a 3-carbon chain onto one of those carbons in my ring. All right, we got the same steps that we always have for our nomenclature. Step 1 is our parent chain. Okay. We saw something similar when we were talking about naming cyclic compounds. We said the ring is that parent chain, right? And same thing here. That benzene ring is going to be our parent chain. All right, so again, our ring is our parent chain. Okay, so that's either going to be that benzene ring, or we're going to make a note here. What we're going to do in a minute is we're going to learn about a few special benzene derivatives that may also be our parent chain. I'll complicate things with those here in a minute. Okay, 2, we're going to find and name our substituents. All right, I'm going to leave a little bit of a space here because we're going to introduce one new one. But for right now, we're going to stick with this example. And we know how to name this substituent right here, right? A 3-carbon alkyl group. This would simply be a propyl group. All right, so I guess I should do my parent chain here. My 6 carbons in my benzene ring. And then I have these 1, 2, 3 carbon substituents. So I have a propyl group on that benzene ring. What's the third step we got to do? Number, yes, number the parent chain. All right. And we have seen before when we were talking about our cyclohexane, our cyclic alkane nomenclature. When we have a mono-substituted alkane, cyclic alkanes, right? Only one substituent on that ring. How did we name that? So let's just do an example. We have a 6-membered ring with a propyl group. How did we number this ring? We don't bother, right? Because if I were to pick up this propyl group and move it anywhere else on that ring, that would just become carbon 1 on the ring, right? So for our mono-substituted benzenes, just like our mono-substituted cyclic alkanes, we can omit that numbering. Okay, and then the last step was to assemble it all together. So this thing here would simply be propyl benzene. All right, my benzene is my parent chain. No, the benzene is all encompassing. The benzene is that cyclic ring with the double bond, single bond, double bond, single bond. That is benzene, that whole thing. So when there's no like straight chain benzene, right? Benzene uniquely points to that ring right there. Yep, so no cyclo, just the parent chain benzene. All right, so let's just do another example here. All right, as well as I'm going to take this opportunity to introduce a new substituent to you guys here. What's called it's got one of the more badass names. This is called a nitro group. It's treated just like our other substituents, not in the back half of the name, but in the front half of the name. Again, this is a nitro group. All right, what do we think this first one's called? Chlorobenzene, exactly, right? We have our one substituent, so I'm not going to bother numbering a chloro group. My parent chain is just that 6-carbon benzene ring, so this would be chlorobenzene. All right, and this thing we just learned about, but again, same sort of idea here. I'm going to find my parent chain. It's going to be that benzene ring. Now I have this new substituent on there, a nitro group. This would just be nitrobenzene. Okay, let's talk about this nitro group here for a second. Okay, let me get rid of my colors. All right, I probably should have had y'all fill in these formal charges in lone pairs because that's one of those things that we learned how to do last unit. All right, we'll notice that our nitrogen in this group has 4 bonds, so it's got that positive formal charge. We have one oxygen that has 2 bonds and 2 lone pairs, so it's happy, it's got its 0 formal charge. But the other one has only 1 bond and 3 lone pairs, so it's got that formal charge of -1. All right? So you look at this functional group and you're like, dang, that's a lot of charge packed in there. What's going on here? Doesn't look all that terribly happy, because in general, molecules don't love to have charges, never mind positive and negative, okay? So there's something really important that helps to stabilize the charge in this molecule, which is what's called resonance. Okay, I can draw this same exact structure of an equivalent structure by swapping the double bonds on my oxygen, right? I have 1 single bonded oxygen and 1 double bonded. I'm just going to swap who's who. Well, that's not going to do it. So now the oxygen on top is the one with the single bond and 3 lone pairs, and the oxygen on the bottom is the happy one with 2 lone pairs and 2 bonds. All right, so notice that what's changed here between these two, if we're just going to play the spot the difference game here, I have moved this pi bond and this lone pair, right? Now my pi bond is down here and my lone pair is up there, okay? These are 2 equivalent structures here, what we would call resonance structures. All right, so our resonance structures. Our electrons are moving to form the equivalent molecule. All right, so my lone pair and my pi bond are trading positions. We have these electrons that are moving, but my net result is just this same equivalent nitro group. All right. Whenever this happens, whenever you can do this, whenever you can draw 2 equivalent structures like this, this always adds stability to a molecule. Most molecules that are stable holding a formal charge, they can get away with it because they have these multiple resonance structures. Okay? In effect, what this is helping doing is spreading out that negative charge so that the negative charge isn't only sitting on one of those oxygen atoms, it's kind of passing it back and forth between the 2 of them, right? So it's spreading out that negative charge, which helps stabilize that negative charge, okay? So this adds stability to our molecule, and it spreads that charge over multiple atoms. All right, back in general chemistry, this would have been like those worst case Lewis structure problems that you would have been given for like a polyatomic ion, and you couldn't just draw one, you had to draw multiple ones. Those are those resonance structures. Okay? So bottom line is we see this in organic chemistry because they add stability to a molecule and they help stabilize charge that may appear in a molecule. Okay, cool. So up here I said that my parent chain was going to be the benzene ring or one of these special benzene derivatives. So what the heck do I mean by that? All right, so now we're going to introduce these special benzene derivatives. All right, these special benzene derivatives, they're just going to be benzene with some sort of a functional group on there. But the whole shtick is that they have their own special names. The reason for this is largely historical. Again, benzene was a very important part in early organic chemistry. So some of these really common derivatives of benzene, they were kind of given their own special name that then when the world got together and said, oh crap, we got to formalize all that stuff. Well, those common names just kind of stuck. They were too widely in use to be replaced with something more systematic. So everybody gave up and said, fine, we're going to call this molecule its own special name. Okay? So one example would be if I stuck an alcohol group on that benzene ring. All right, we haven't gotten there, but we'll talk about how to systematically name alcohols, but this, you wouldn't follow those rules. This has its own special name. This molecule is phenol. P-H-E-O-E-N-O-L. Phenol. Okay, that OL ending is something that's common to alcohols, but again, this molecule all by itself has this own special name. All right, now let's stick another functional group on this benzene ring here. All right, what do we call it when we have these carbonyl bonds that are at the end of our molecule? What is our functional group here? An aldehyde, not a ketone, but an aldehyde. And so this molecule here is benzaldehyde. All right, cool. Let's put this functional group on here. Another carbonyl bond, but now I'm going to add an OH to that carbonyl carbon. What's that functional group? So ketone would be if it was a carbon over here, but when it's an OH, it's got another special name. Carboxylic acid, all right? So this here is benzoic acid. So these three right here aren't too bad. Again, alcohols with an OL ending, that checks out. Benzaldehyde literally has the functional group name in its name, the aldehyde. And benzoic acid is that carboxylic acid group. These other two kind of come out of left field, but we have a little bit of a helpful way to remember them. Okay? So first one would be if I put an amine group on that ring. NH2. All right, this is what's called aniline. All right, and does anybody remember our functional group where we have oxygen not at the end with a hydrogen, but sandwiched in the middle between two carbons? This is an ether, and this molecule's name is anisole. All right, so like I said, these two kind of come out of left field here, and they're both very similar, aniline and anisole. So they seem like they're going to be really easy to get mixed up here. Okay. One thing to note is that aniline, with the N in the name, is the functional group with the nitrogen, with the N, and anisole, with the O in the name, is the functional group with the oxygen in there. Okay, so very similar sounding, but one little key thing that we can kind of help to trace back to remember who's who here. So these are our 5 special benzene derivatives. Okay. All right, so we're going to incorporate these here. What's up? There are. I got lazy. I'm sorry. Definitely oxygen always with its 2 lone pairs. Yep. Cool, so we're going to kind of roll this into what we were discussing with names, but we got one more thing to throw in there. We talked about how to deal with mono-substituted benzenes, all right? But now we need to talk about di-substituted benzenes. Okay, so for example, we said if we stuck 1 chloro group on there, that would just be chlorobenzene. Okay, but what about when we stick 2 chloro groups on there? Now how do we deal with it? All right, so somebody said one key component here, this is going to be dichloro. Okay, but I still have to indicate where these 2 chlorines are relative to one another around this ring, right? In this case, they're right next to each other. That would be a different molecule than if I picked this chlorine up and moved it 1 carbon away. And that would be a different molecule than if I put those 2 chlorines on opposite sides of the ring. Right, so these are all dichlorobenzenes. They all got that part of the name in common. Okay? But again, we have to have something in our name that indicates our spacing. And this is where our analogy to our cyclic alkanes kind of breaks down. If these were cyclic alkanes, we would just do our normal numbering scheme, right? Great. Well, with benzene, unfortunately, it's not that simple, okay? We have some new terminology that we're going to learn with regard to our spacing here, all right? The directly next door to one another substituents, we call these ortho to one another. Okay, so ortho means next door neighbors. When we got one removed, so now we have an empty carbon in the middle of these two here. This is what's called the meta position. And when they're on opposite sides of the ring, this is what we call the para position. All right, so for our di-substituted benzenes, we don't use our normal numbering scheme that we've learned how to do. Instead, we use this terminology ortho, meta, para. Okay? Ortho means they're next door neighbors. Meta means there's one removed, there's one blank spot in the middle, and para means they're on opposite sides of the ring. Okay? So here are three examples. How I kind of remember this is, all right, I say, all right, there's one thing on this ring. What's up?
So even though they're not numbers, we have to put the hyphen between?
You do still, yes. Yep. Good question. Yeah, normally we reserve the hyphen for separating letters and numbers, but no, for these ortho, meta, para, they kind of take the place of the numbering. Okay, so if there's one thing on the ring here, the positions right next door are those ortho positions. One more removed are those meta positions. And then the one that's located on the opposite side of the ring is the para position. Okay, so our order is O, M, P. Like OMG, but OMP. All right, again, sometimes if you can remember the dumbest thing, it'll stick in your head for absolutely ever. Say it like a Valley girl and it'll stick in there even more, right? OMP, that's the order that we gotta remember, right? But this is what we use for our di-substituted benzene. We don't use our normal numbering scheme that we're used to seeing. We're going to instead use these ortho, meta, para designations. Okay, so let's just add to our nomenclature list. We said for mono-substituted, we get to omit the numbering. For di-substituted, we don't number. Instead, we're going to use that ortho, meta, para designation. Okay, and you will see these, just to note here, ortho dichlorobenzene, perfectly acceptable. You will also see it just abbreviated O dichlorobenzene. Perfectly fine. Both of these would be accepted in your homework. All right, or for meta, you would just see it M dichlorobenzene. Importantly, when we say it out loud, even if it's M dichlorobenzene, we would say meta dichlorobenzene, right? We know what those O, M, and P stand for. So para would be the P dichlorobenzene. All right, what's up?
I missed the part where you spell benzene incorrectly.
Where I spelled benzene incorrectly? Did I?
Benenes.
Say it again?
This is dichlorobenenes instead of benzene.
Oh, I see. No, that was just me not knowing how to
Okay.
spell. And then copying and pasting it wrong everywhere.
Okay, I was just like, how are we supposed to do that?
No,
Okay.
spelling is not really my forte. But no, I just made a copy and paste mistake here. Benzene. Not Benize, ever. Just benzene.
So just the abbreviation will be marked correct in our homework?
Correct. Either one, both of those are built in for these examples. Yep. Okay, cool. So now we're going to keep in mind two things. Go for it.
I just had a question. Which one is like more used, like written out or just the letter?
I don't know. I think you will see both. I guess like when you're looking on the back of your shampoo or something, you're more likely to see it abbreviated as. We don't like writing, right? So more likely you probably see the abbreviations quite a lot. But again, importantly, we always say ortho-meta-para. So even if I read this, I would still read it as ortho-dichlorobenzene. Okay, so now we're gonna do some more practice on our nomenclature. But importantly, we're going to incorporate two things. One, what we learned about our spacing here for our di-substituted benzenes, right? Our ortho-meta-para designation. But also the fact that if you see one of these 5 special functional groups in that molecule, it's no longer benzene as the parent chain. It's going to be one of these names here. Right? So if I see an OH group in that molecule, it's no longer benzene as my parent chain. It's this special name right here, that phenol group. Okay? The only dash is going to be between that orthometapara and the rest of it. Everything else is going to get run together. All right, let's do this first one here. Importantly, what is my parent chain in this molecule? Yeah, that whole thing, right? Not just the benzene ring, but including that one. We got that one of those special OH groups in there, one of those special functional groups, right? So that right there matches one of my 5 special benzene derivatives, which means that my parent chain is no longer going to be benzene. It's going to be the name of that special derivative. Okay? So that whole thing is my parent chain. My parent chain would be phenol. I got this substituent over here, this chloro group. All right, and importantly, these are 1, 2, 3 carbons from one another, which we call what? Meta. So this would be meta-chlorophenol. Okay. There's the dash between that orthometapara and the rest of the word. Everything else gets run together. What's my parent chain over here on this next example? Benzoic acid, right? Again, it's one of those special benzene derivatives, so it's not just the ring, but also this whole thing here, and that's got its special name, benzoic acid. Okay, now I think I understand what you were saying, but let me just get to there, okay? The other part, what's my substituent here? A propyl group. And this propyl group is located where compared to that benzoic acid group? Ortho, meta, or para? Para. So this would be parapropyl benzoic acid. And there is a space between the word acid and the rest of the name. Sorry, is that what your question was? I got it. I thought you meant the propyl and the benzoic. Those get run together, but there is a space between benzoic and acid. One of our few functional groups, and we haven't really even gotten there yet, that have a space in the name are these carboxylic acids, because they got that word acid on the end. So parapropyl benzoic acid rolls off the tongue. All right, so then this one here, what's my parent chain? The aniline. Importantly, this nitro is treated like a substituent in our chemistry here, in our nomenclature. So kind of like a chloro group or a propyl group, this is just now a nitro group. My parent chain includes that special functional group, that NH2, making it aniline, and the nitro group and the NH2 are located where from one another? Ortho. So this would be our ortho nitroaniline. Okay, cool. So if we have one of those special benzene derivatives in there, one of those special functional groups on those benzene rings, it changes the name of that parent chain, all right? So we got these 5 special benzene derivatives. I know that memorization's kind of a pain in the ass. You're going to have an assignment where you're going to be shown one of these and you're going to have to fill in the name. Okay, great. Take it with your notebook open the first time, get your max points, right? But you can repeat that assignment strictly to help you memorize that sort of stuff. Make sure you can do that assignment with your notebook closed, and then congratulations. You know your 5 special benzene derivatives here. Okay? So then, just to make things fun, I'm going to introduce 2 more. But these are what we're going to call the not special benzene derivatives. Okay, so what do I mean by not special? These are molecules, we got to recognize them. They have their own special unique names, but they're not going to be our parent chain. They're not going to plug into the rest of our nomenclature. These are just one-off. If I show you this molecule, you got to know its own special name. Okay, so the first one, for example, is not a red line, but rather, let me copy and paste my nice ring. If we stick a methyl group on benzene, you would think that would be methylbenzene based on everything that we studied up until this point. But no, they don't make it that easy. All right, this thing has its own special name. This thing is toluene. And if you stuck anything else on that ring, it stops being toluene, all right? But just that one molecule right there, you got to recognize as having a special name, toluene. All right, and truthfully, I'm lying to you a little bit. You will see that sometimes it is the parent chain and sometimes it isn't, and there's a way more complicated set of rules that we're going to gloss right over right now, and I don't want to get into all of that. So what I need you to be able to do is recognize this molecule right here as being toluene, okay? And the last one is if we stuck 2 methyl groups on there. It's not dimethylbenzene, but also has a pretty cool name. This is xylene. All right, but there are actually 3 different xylenes. How is that possible? Let me show you one other one. These are both xylenes here. What's the difference? That ortho-meta-para business, right? So both of these are xylenes. Our first example is orthoxylene. The other one is metaxylene. And I believe in y'all at this point. You're going to put in your notes on your own, paraxylene. So we have them all down here. Okay, so here's our list of the not so special benzene derivatives. What I mean by that is we need to be able to recognize them. But they are not the parent chain. When we have our derivatives with other substituents, let's say. All right, so we need to be able to recognize these not so special benzene derivatives, but they're not going to be our parent chain if we start sticking other substituents on the ring. Okay, so toluene and xylene are methylbenzenes. They, for historical reasons, have their own special names. Okay, Typically, a lot of the work that you used to do with benzene back in the day, before they realized it was so terrible, they now do with toluene instead. It turns out that that one methyl group makes it not as good as wiggling its way into your cells.
So would adding another one just bring it back to trimethyl?
Yeah, all of a sudden now we have kind of a different thing. We didn't talk about tri-substituted benzenes for a reason. I will say if you do get up to more than 3, then you just start numbering like normal, but we're gonna leave it at 2. Okay, cool. So now that we talked about a bunch of bookkeeping stuff for our benzene derivatives, let's start talking about our chemistry of benzene. All right, and the very first thing that we're gonna have to do is remember something very important about our alkenes, because of course benzene is just a ring with a bunch of double bonds in it, okay? When we were talking about alkenes, we brought up this picture here, which I understand is a little bit of a scary image to be showing this little balloon structure here. It's like, what the heck is going on there, okay? Importantly, when we talked about our alkenes, we talked about how there were these 2 different types of bonds. That double bond, those 2 bonds are not identical. The one of them is what we just call a sigma bond, right? And that's what's pictured here in orange. And your sigma bond is kind of what you would expect for a covalent bond, right? Covalent bonds are a shared pair of electrons. A sigma bond is when 2 bonding atoms are sharing a pair of electrons between the 2 atoms. Checks out, right? That kind of makes sense. The pi bond, the other one, is really the weird one. That second bond in a double bond, it is not located between the 2 atoms that are bound together. It's located above and below. Right? So my pi bond here is this overlapping region. The overlap between these 2 peanut-shaped orbitals is what forms my pi bond. All right? With regards to alkenes, this is what made alkenes so much more reactive than alkanes. They got a pair of electrons sticking above and below the molecule where they're really easily accessible. All right? But now remember, when we're talking about benzene, now all of a sudden we have not just one double bond, but a whole lot of double bonds next to one another. All right? So each one of these then has 1 sigma bond and 1 pi bond. Okay? So if we kind of extend this thing, right, that means that every carbon in there has a little purple balloon extending above and below this little peanut-shaped orbital here. If we do that all in a ring, all right, I'm going to tilt my benzene ring on the side. Let me actually get it. Right? Each one of those carbon atoms has one of those little purple peanut-shaped balloons on it, or what is better represented in our textbook image here. Okay? Cool. So that means that our pi bonds here are going to be between these 2 neighboring carbon atoms in our molecule, extending above and below the plane of that ring, right? These rings are flat. They got these balloon structures of electrons sitting above and below the ring where those pi bonds live. Okay? Now, benzene really stumped people for a long time, all right? Early on, some of the earliest techniques that we had in chemistry is we could figure out the molecular formula for a molecule, right? So we knew this molecule was C6H6. We knew it was in this ring here, okay? And the other thing that they can do is they can do what's called X-ray crystallography, where they can get a sense of how far apart atoms are in a molecule. And one of the earliest things that were known, so again, we're talking about benzene structure. All right, is that double bonds are shorter than single bonds. All right, so what you would expect for benzene to look like here. And I'm going to kind of exaggerate here, is to have these really long single bonds separating these much shorter double bonds. All right, and again, I kind of exaggerated these for effect here, but you would expect this asymmetric kind of structure here. We would expect every other bond to be short, and then in between were these longer bonds. And then they stuck this thing in their little X-ray crystallography machine, and it turns out that in reality, all of those bonds are the exact same length. Right? It is a perfectly symmetrical hexagon structure. Where these are the same length here. Okay? So remember before we were talking about our nitro group and we talked about these resonance structures, how these electrons can move between these multiple positions. This was a theory that was really first developed to help explain what the heck was going on with our benzene ring. All right? If we look at our little balloons here, we have every other one is a pi bond. All right, but importantly, every single carbon atom has one of those p orbitals, has one of those peanut-shaped orbitals. So the electrons aren't going to stay still between those two carbons. They're going to spread themselves out across this entire ring structure here. All right, let me see if I can't represent that a little bit neater. Right, so this pair of electrons doesn't just live here between these two carbon atoms. They're going to spread themselves out across this entire ring structure here. Okay, so that means for our benzene ring, we're going to get lazy and always just draw one structure. But if we were being really good, we would draw our two different resonance structures here. All right, and what I'm going to do is I'm going to rotate this so that now my double bonds have sort of migrated. This represents the true structure of benzene here. Those double bonds are not what we would call localized. They're not stuck in one position. They're able to spread themselves out to both of these positions. Okay, so these are our resonance structures. All right, outside of chemistry, you will often see benzene represented as a ring, and then instead of showing the double bonds, they'll show like this little checkered circle in the middle here to represent that those electrons are actually spreading themselves out and moving around and around and around that ring. We hate this in chemistry. It does not do a good job of properly displaying the number of electrons that are there, so it's not really something that we use. We always just pick one of these two structures above, but nonetheless, it does a good job of kind of illustrating what I'm talking about those electrons not staying put, but being delocalized. They spread themselves out across that ring, okay? So our electrons spread out across all of those peanut-shaped orbitals. Okay? We talked about our geometry of alkenes, and all we've done is now extended that to this ring structure here. We see that then every carbon in that ring has that little peanut-shaped orbital all lined up perfectly, all right next to each other, and so those electrons can spread themselves out across all of those orbitals. Because of that, remember we said those resonance structures, they meant that that nitro group was nice and stable, right? Same thing here. Benzene is a remarkably stable molecule, right? Way more stable than what you would expect based on sort of calculations. Because these electrons aren't staying put, they're able to spread themselves out. And resonance is good for stability. Okay? So this leads to this phenomena called aromaticity. This is this extra super stability. When electrons can spread themselves out across a ring. Okay. We got a fancy terminology for this spread out across all peanut-shaped orbitals business. This is what we call conjugation. All right, these bonds are conjugated, meaning these bonds are talking to one another. Spreading out those electrons. All right, so benzene is our quintessential example of an aromatic compound. All right, and in order to be aromatic, you got to satisfy these two rules. Number one, you have to be a fully conjugated ring. Meaning all atoms are sp2 hybridized. Okay? So first of all, in order to be aromatic, you have to have a fully conjugated ring, which strictly speaking means all those atoms have to be sp2 hybridized. Why? Like, where the heck did that come from? Because you need every atom to have these little peanut-shaped balloons that the electrons can spread themselves out to, right? If you're sp2 hybridized, that means you have this little peanut here. And in order for the electrons to make their way around and around and around this ring, everybody in that ring has to have one of those peanut-shaped orbitals. If any one of those atoms in the ring is not sp2 hybridized, doesn't have that balloon in there, it's going to mess up the ability for the electrons to spread themselves out. So if, let's just say, we took away one of these, we're going to make this guy not sp2 but sp3 hybridized. Well, now the electrons, they can still spread themselves out like over here, but they can't get the full way around the ring. And when they can make it the full way around the ring, that's that extra special aromaticity, aromatic. Okay? And then the next one is a little bit weird of a rule, sort of comes more from a theory standpoint here, or at least requires to understand. Rule number 2 is there has to be an odd number of delocalized electron pairs. if a compound meets these two rules right here, then it is an aromatic compound. Okay?
Can you describe like the odd number of the...
Yeah, we're actually going to kind of mostly save this one for next class, and we're going to focus real heavy on that first rule, and then we'll pick up there next lecture. Okay? Cool, so I'm going to put down some structures here, and we're going to see whether or not it satisfies or fails this very first rule in our list of what it means to be aromatic here. Okay? We'll take our classic benzene. All right, so we're trying to say whether or not these meet or fail that first rule, a fully conjugated ring. So in order to tell whether this is a fully conjugated ring, I want to go through and I want to mark all of my sp2 hybridized carbons, right? So if they are about a double bond, they're going to have that proper hybridization. So these are sp2, these are sp2, and these are sp2, so do I have that fully conjugated ring? Check, check. Benzene is indeed a fully conjugated ring. All right. Now I deleted one of those double bonds in the middle here. So now again, we got to go through. Do we have a fully conjugated ring? These carbons right here are sp2 hybridized. These ones are sp2 hybridized. But both of these right here are sp3 hybridized. They both have not one, but two hydrogens sticking off of them, right? So these right here will break that ring's conjugation. I do not have a fully conjugated ring. This right here fails rule 1. And we got a special name for molecules that fail rule 1. These are what are called non-aromatic compounds.
Wouldn't it just have one carbon that's not, because the other one's still part of the double bond?
So 4 of the 6 carbons are on either side of the double bond, but both of these up here do not have a double bond associated with them. So if I just kind of get rid of my markings here.
Isn't it just one away though from a carbon, double bond still count on that bond, or no?
No, so these, in terms of my conjugation, this one actually has 2 hydrogens here. This one has 2 hydrogens, which means that they're sp3. They don't have one of those balloon-shaped orbitals anymore if they're sp3 hybridized. Yeah, so both of these are going to mess up my ring here, my conjugation. All right, so then we get to this one here. Now we have only a 5-carbon ring, but I'm going to play the same game. I need it to be fully conjugated. So I'm going to mark all of my sp2 hybridized carbons. But then I get to this one here, and again, this is sp3 hybridized. So this thing breaks up my fully conjugated ring. So what would we call this type of molecule? Non-aromatic, right? Molecules that fail that very first rule, we simply call non-aromatic. What about the square with the double bonds here? Our cyclobutadiene. Does this fall? Let's just take a vote here. Satisfy rule 1 or fail? Who thinks it satisfies? Cool, right? So this carbon and this carbon are about a double bond. This carbon and this carbon are about a double bond. So indeed, I have a fully conjugated ring. Check, check. That one satisfies rule 1. And then lastly, this one here. Now we have the very similar to what we saw above, but now that top carbon is a carbocation. Okay? So first of all, I'm going to go do my conjugation here. These ones are definitely sp2 hybridized. And one very important thing that we have to remember about carbocations is carbocations are also always sp2 hybridized. They actually have an empty p orbital, right? So instead of having one of these balloons that are filled with electrons like these other guys, now it's empty, but it still does not break up the conjugation of that ring. That empty p orbital can accept electrons. All right, so importantly, our carbocations, we're just going to make a special note here.
It would want to accept the electrons.
It absolutely would, yeah, and those electrons are going to bounce around, and that's also going to move the positive charge. So you see these electrons are just going to spin and spin around this ring. So we're going to just make note, carbocations are sp2 hybridized, i.e. they do not break a ring's conjugation. So this indeed would also satisfy rule 1 here. I have a fully conjugated ring. Okay, that carbocation is not going to mess up that ring's conjugation like, say, an sp3 hybridized carbon would. Okay, so this one's a check, check. Okay, so if a molecule fails rule 1, we call it non-aromatic. If it passes, we got to move on to rule 2, and we'll talk about rule 2 next class. Okay. Remember the one thing I forgot to say about your exams, which is that you can expect to see your grades next week. Okay, they'll be posted over the weekend, and you can see your exams next week.